Welcome back to AI Tactiles. In today's video, we're diving into two crucial concepts in statistics: skewness and kurtosis. These measures help us understand the shape of our data distribution, which is essential for accurate analysis. Let's start with skewness, also known as asymmetry or distribution skew. Skewness measures the asymmetry of a distribution. In simpler terms, it tells us whether the data is stretched more to the left or the right. A distribution can be left-skewed, right-skewed, and symmetric distributions. Let's start with negative skew. Negative skewness, also known as left skewness, occurs when the left tail of the distribution is longer or fatter than the right tail. In simpler terms, the distribution has more values on the right side, and the tail extends further on the left. In a negatively skewed distribution, the mean is typically less than the median, which is less than the mode. This is because the mean is pulled towards the longer left tail. Common examples of negative skewness include test scores where most students score high in easy exam but a few score very low. Here's a visual representation. Notice how the bulk of the data is concentrated on the right, while the left tail stretches out. This is a classic sign of negative skewness. Next is positive skewed. Positive skewness, also known as right skewness, occurs when the right tail of the distribution is longer or fatter than the left tail. Essentially, the bulk of the data is concentrated on the left, and the tail extends further on the right. In a positively skewed distribution, the mean is usually greater than the median, which is greater than the mode. The mean is pulled towards the longer right tail, affecting its position relative to the median and mode. Here's a visual example. An example is the age of retirement, where most people retire around the same age, but a few retire much earlier. A symmetric distribution is one where the left and right sides of the distribution are mirror images of each other. This type of distribution has zero skewness, meaning it is perfectly balanced around its center. In a symmetric distribution, the mean, median, and mode are all located at the center of the distribution. This indicates that the data is evenly spread out on both sides of the central peak. Here's a visual example. Notice how the distribution is evenly distributed around the center, with the left and right sides being mirror images. This is a classic sign of a symmetric distribution or zero skewness. Common examples include the normal distribution, also known as the Gaussian distribution, and the bell curve. These distributions are symmetric, with zero skewness, reflecting a balanced spread of data. Zero skewness values are close to zero, indicating a symmetric distribution. Positive skewness values greater than zero indicate a right-skewed distribution, and negative skewness values less than zero indicate a left-skewed distribution. Let's briefly touch on the Pearson coefficient of skewness, a useful measure for quantifying skewness. It is also known as the Pearson skewness coefficient or Pearson's measure of skewness. The Pearson coefficient of skewness can be calculated using the following formula, where x bar is the mean of the data, median is the median of the data, standard deviation is the standard deviation of the data. This formula helps us quantify the degree of skewness in a distribution. Let's look at a quick example. Suppose we have a dataset with a mean of 50, a median of 45, and a standard deviation of 10. Plugging these values into the formula, this positive skewness value suggests that our data is right-skewed, with a longer tail on the right side. Next, let's talk about kurtosis. Kurtosis measures the tailedness of a data distribution. It indicates how heavy or light the tails of the distribution are compared to a normal distribution. It's an essential tool for understanding the extreme values or outliers in our data set. Kurtosis can be categorized into three types: leptokurtic, platykurtic, mesokurtic. Leptokurtic distributions with heavy tails and a sharp peak. They have a kurtosis greater than 3. Platykurtic distributions with light tails and a flatter peak. They have a kurtosis less than 3. Mesokurtic distributions that are similar to the normal distribution. They have a kurtosis of exactly 3. The formula for calculating kurtosis is, where n is the number of data points, xi represents each data point, x bar is the mean, s is the standard deviation. Let's look at an example. Suppose we have a dataset and calculate a kurtosis value of 4.2. This suggests that our data distribution has heavier tails than a normal distribution, indicating a leptokurtic distribution. So, why should we care about skewness and kurtosis? These measures help us identify the underlying characteristics of our data distribution, which can impact the assumptions and effectiveness of statistical analyses. Applications in data science. In data science, understanding skewness and kurtosis can improve model performance and ensure our data fits the assumptions of various statistical tests. For instance, if our data is heavily skewed, we might need to transform it before analysis. Thanks for joining us today. If you found this video helpful, don't forget to like and subscribe for more content on AI and data science. See you in the next video.